So today, my topic is green synthesis and photocatalytic activity of chitosan-coated iron oxide nanoparticle. Myself, Dr. D. Ilakkam, Assistant Professor from Department of Biotechnology, Mother Teresa Women's University, Kodaikanal, Tamil Nadu. So that nanotechnology is an emergent field to search for a new nanoparticles that shows a various shape, size, and other properties. Nowadays, research trends recommend the use of nanoparticles for various several jobs with which is very high efficiency. Nanoparticles have a minimum of one dimension nanoscale in the range of 1 to 100 nanometer. So in order to synthesize this new nanoparticle to have different shapes and size, there are different techniques available, which is categorized into two physical approach and chemical approach. Coming to physical approach, it is also called as a top-down approach, which includes diffusion, radiation, thermal decomposition, ARC discharge, etc. Then coming to bottom-up, it includes seeded growth, polyol synthesis, electrochemical synthesis, biological entities for fabrication, and chemical reduction. So among this technique, the most common technique is chemical reduction, and this method pose a environmental and biological risk due to expensive and use of hazardous chemicals. So in order to replace these physical and chemical methods, biological methods pave the way to synthesize the nanoparticles in eco-friendly manner. So the biosynthesis of nanoparticle is an interesting area by possessing application in various fields like optic fibers, electronics, biomedical, biosensors, and other areas. And the presence of phytochemicals in plant extract show a potential ability to reduce the metal ions within a short period as compared with other normal natural material like bacteria, fungi, and proteins. So the plant mediated nanoparticle is a leading process because of its rapidity, simplicity, and avoidance of contaminant. So hence the plant material I have chosen as a potential source for the metallic nanoparticle synthesis. So this is the plant material, Perogonium gravulonis. So this is a um, um, geranium crop, and this geranium crop is able to grow in a high altitude and milder climate. So it is also come up very well mainly in the Nilgiris and Kodaikanal hill, which is a hilly region of Tamil Nadu, and also it is found in the Bangalore in Karnataka, which is about in the area of 2000 hectare. So this aromatic shrub can reach up to the height of 70 centimeter and lateral of 90 centimeter. So nowadays there is an application of this nanoparticle in industries. So the organic dye present in the industrial effluent and other waste steam possesses a serious environmental problems and have predicted as a carcinogenic material. So there is a various techniques available for the removal of these chemicals, but recently nanoparticles are considered as a potential agent to treat the organic pollutant from the wastewater to treat the dye. So there are certain limitations to the application of nanoparticles for the removal of dye called azo. So the synthesized nanoparticles are coated with biopolymeric substances so that it will enhance the degradation activity very quickly. So in my study, I have chosen chitosan, which is a modified natural biopolymer obtained from deacetylation of chitin, which contains hydroxyl group as a functional group. So chitosan has a ability of biodegradable and also have antibacterial activity and has an excellent film forming property. So based on this basic idea, I have framed my work. So in my study, the iron oxide nanoparticles were synthesized using this plant, that is Pelargonium and gravulonis, and it is characterized for various spectral studies like UV vis, Fourier transform, IFTIR. So after that, the synthesized particle is coated with chitosan And I have checked the synthesis of nanoparticles using this leaf extract, Pelargonium graveolens. So in this, I have prepared the ferric chloride as a standard. So I have added equal amount of plant extract and ferric chloride, and I have incubated at room temperature. So this yellow color is converted into a black color. So I have checked this whether it is a nanoparticle or not in a UV vis spectroscopy. So this presence of this absorption peak prove that the nanoparticle is synthesized in this using this leaf extract. Then afterwards, I have checked whether this nanoparticle coated with, I have coated this nanoparticle with chitosan. So whether this chitosan is having the degradation capacity of this Congo red, since it is a prevalent dye which is present in a textile industry. So I have chosen this Congo red. So this I have prepared various concentration of nanoparticle, and I have incubated. So this color change itself, so the removal of color change is positively correlated with as the concentration increases. Then afterwards, so the same nanoparticle which is coated with the chitosan. So this is a chitosan alone. I have performed this experiment, and then I have performed the experiment, same experiment with chitosan coated iron oxide hybrid composite. So compared to the chitosan, where if the nanoparticle combined with the chitosan is degraded very fast, and I have quantified the same procedure. I have qualitative and quantitative analysis we have carried out. After analysis this, then we have performed the antibacterial activity for gram-negative bacteria. So among that, the Klebsiella pneumonia showed a better result when compared to other Bacillus, Pseudomonas, Enterobacter. So based on this, I have concluded that iron oxide nanoparticle chitosan composite demonstrated superior decolorization performance when compared to the chitosan alone. And this study undertook the simplicity and expediency and cost effectiveness of green approach to synthesizing the iron oxide nanoparticle and hinting at promising avenues sustainable application. Thank you.
Okay, thank you for your presentation.
The series configuration is having the NMOS transistor having A and B, and similar A and B have been placed in the case of parallel configuration in the case of PMOS transistor or the pull up transistor point of view. So this is the basic orientation of the NAND gate based on digital CMOS logic circuitry. So here, in the case of Cadence platform, what we have got, the circuit, if it is clearly visible from the circuit, the NMOS, these two NMOS is having the length of 100 nanometer with a width of 120 nanometer, and these two PMOS, which are placed in the parallel configuration, they are basically having the width of 250 nanometer, that is almost 2.5 times or 2.3 times over the NMOS width. So this is basic the circuit or schematic of the NMOS circuitry in the Cadence Virtuoso platform. It is a symbol has been generated by the cell view command in the case of Cadence Virtuoso software platform, and it is the basic truth table. And here the simulation has been performed for the case of two input signal, that is VA and VB, and the output is basically denoting from the drain terminal of this PMOS network and the NMOS network. And here the VA signal is considered over a pulse width of 30, that is the period of 60 nanosecond, and 20 nanosecond period for the case of the input signal B. So based on that, when we are telling the overall output circuitry or the output waveform or the transient analysis, it has been observed that over the x-axis it is basically 200 nanosecond, and as the truth table of the NAND gate is familiar to all of you, when it is basically 0 0 it is 1, when 0 1 it is 1, when 1 0 it is 1, and when 1 1 it is 0. So therefore when this particular dotted portion is basically representing, see here A is representing in the red color waveform, B, the second input, is representing in a green color waveform, and the pink one is basically the output section. So when the red is logic 1, the green, the B, is also logic 1. As per the truth table, the output should be 0. So here the pink portion is also denoting the output is 0. Similarly, when the input is 0 and the second input is also 0, that time the output should be 1. So when the A and B both are 0, that time the output should be 1. So here the same thing is also reflected. So the overall characteristics or the transient characteristic, why it is called transient characteristic? Because with respect to time, we are measuring the output waveform, providing the pulse input A and B, where the V1 level is basically 0 and the upper limit is V2 is level is basically 1, having the rise time and the fall time of 50 picosecond. So these two waveform of A and B provided such a output which is totally validated from the truth table. So the output is also correlated with respect to truth table and denoting the output is correct form. Similarly, in the case of NOR gate, as the Boolean equation of a NOR gate is basically A plus B whole complement. So definitely the pull down network should be the combination of A plus B, that is the parallel combination of the one NMOS transistor with the another. So here the one NMOS transistor is having the input as a A and the second NMOS transistor is having the input as a B. And the dual from, that is the parallel network, will be converted into the series combination. So the PMOS network is having the series combination of the MOS transistor having A input and the MOS transistor having B input. So this is the overall schematic circuitry of the NOR gate in the background of Cadence Virtuoso platform. The symbol is generated from the cell view command, which is basically denoting the NOR gate symbol, and it is a truth table. This case also I have also considered the waveform or the overall pulse width or the period in such a way that for the case of A, it is basically 60 nanosecond period, and for the case of B, it is basically 20 nanosecond. So coming to the validation of the result, as we all know, the truth table is representing in this via this truth table, where 00 is denoting 1, 01 is 0, this kind of thing. So now see, the red waveform is the input A, the green one is basically the input B, and the pink one is basically the output. So when both the input, that is A and B, are at logic 1, at that time the output is 0. So therefore, when both the inputs 1 and 1, so output is 0. So it is, this part is validated from this row. Similarly, when it is basically 0 and 0, that is when both the inputs are 0, at that time the output should be 1. Here the pink one, that is the output section, is also denoting as a 1. So this different two waveform, which is basically the input terminal of the corresponding NOR gate, provided the proper output, which is basically the correct output with respect to the truth table. So the NOR gate is basically simulated over the transient response of 200 nanoseconds, having the rise time and fall time of 50 picoseconds. So the output is totally validated for both the case of NAND gate as well as for the case of NOR gate. So in conclusion, so basically the design and simulation of NAND and NOR gate is basically providing the valuable insight into the dynamic behavior with respect to time, their behavior for the case of transient analysis. And here the width of the PMOS and NMOS have been considered in such a way that 250 nanometer for the case of PMOS and 120 nanometer for the case of NMOS, having the length of 100 nanometer with a technology node of 90 nanometer. So the dynamic behavior is totally validated with respect to the truth table, which denotes the logical correctness or the functionality correctness of the these two logic gates or the universal logic gates. So this paper or this tutorial basically offering how to design, simulate, perform the transient analysis of these two universal logic gates, and without, because in the case of standard CMOS circuitry, the tutorial or this kind of thing is readily available. But in the case of universal logic gate, these papers or this tutorial paper will give you the definitely the overall idea how to process, how to design, how to simulate, and overall validation how you can carry out in the performance parameter with respect to rise time, fall time, or this kind of thing. So this is the overall novelty of this work. So these are the references I have basically used. And finally, thank you.
Good afternoon, everybody. I'm Dr. Jagdish Chandra Mahato. Yes, I'm Dr. Jagdish Chandra Mahato, Assistant Professor in the Department of Physics, Vishwabharati, Shantiniketan, West Bengal. Today, I shall talk on unveiling the potential of two-dimensional V2S2 monolayer as a high-performance anode material for metal ion batteries. So, yes, so this is where we are located at Santiniketan, Vishwabharati, in the Birbhum district of West Bengal, which is 160 kilometers north from Kolkata. This university was founded by Rabindranath Tagore in 1921. This year is a pride moment for the university because UNESCO has recognized this university as a living heritage university. Rabindranath Tagore believed in open air education and introduced that system in this university, and still today, this system is prevailing here. So these are the few glimpses of the university. Many notable persons are the alumni of this university. I would like to invite you once visit this university. So motivation. In these recent years, the quest for advanced energy storage solution has led to extensive research in the development of high performance anode material for rechargeable metal ion batteries. The emergence of two-dimensional material has offered a promising avenue for exploring novel electrode candidates with exceptional properties. Among different two-dimensional material, graphene, modified graphene with different transition metal dichalcogenides such as molybdenum disulfide, tungsten disulfide, vanadium disulfide, and also different metal carbide and nitride, which is categorized as MXene, has manifested as a potential candidate for electrode material in metal ion batteries. In this present work, unveils an investigation into the feasibility of utilizing the V2S2 monolayer as a highly efficient anode material for metal ion batteries using density functional theory VASCODE. So what we do to check the feasibility of a material is given in this flowchart. So at the beginning, we check the geometry optimization of the structure and then do electronic calculation for the density of state and band structure calculation, and then check the thermal stability of that monolayer sheet by phonon calculation, then do the electron localization function calculation to get idea about the electron density on the surface of the monolayer, and then check the possible absorption site on the surface and get the favorable absorption site. Then calculate the electronic band structure of the metal atom absorbed monolayer.
Sir, your PPT is not changing.
Sir, yeah, sir, you are still on the first slide.
Sorry, sir.
You are still on the first slide.
Not yet, sir.
No, sir.
Sorry. Is it? Is it changing?
The slides are visible, but first slide.
Now it's changing, right?
No. I think, sir, you go to the full screen mode and then you change your slides.
Yeah, I'm showing the PPT. I mean the PDF, right?
Yeah.
So still not changing.
No, sir.
Let's try with the PPT. Now, sir.
Yeah. Yes. Your map is visible now.
Okay, okay. So this is the location of the university which I was talking. Is it changing now?
But that map slide is there.
Oh, sorry. now?
No, I think you have to click on the slide numbers in the left column bar.
Okay.
Yeah, now slide motivation slide is there.
Okay.
Yes.
Thank you. Thank you.
Yes.
So these are the steps which we generally follow, which I was just talking. So this work on the prediction or checking the feasibility of V2S2 monolayer as a anode material is motivated from the work which is published in Computational Material Science, which is done on NB2S2 system, published recently. So yes, this is at the beginning. We do the electronic band structure calculation of the pristine V2S2 monolayer, and we see that it shows a metallic behavior from the electronic band structure and density of state calculation using DFT VAS code. Then this is the A shows the geometry optimized 3x3x1 supercell of the V2S2 monolayer. Top view and bottom and side view is shown in figure A. B shows the electron localization function plot, and C and D shows the ICRTMD calculation, where we plot the potential energy evolution during the ICRTMD simulation. ICRTMD means ab initio molecular dynamic simulation at 300 degrees Celsius and 500 degrees Celsius, which gives us that the structure is quite stable in this temperature range. Then we calculate the absorption energy using this formula for the metal ion. We take 3 different metal ion, that is lithium. We checked it for lithium, sodium, and potassium at different possible absorption site. We take the hollow side, we take the on the vanadium side, and on the sulfur side, and also above the vanadium sulfur bond. And from the absorption energy calculation, we found that the hollow site is the most favorable for all the metal absorption cases, for that means for lithium, sodium, and potassium. So this figure shows the geometry optimized single atom absorbed on the most favorable side, that is the hollow side. So after the absorption of the metal, we can see that the structure, the hexagon above which it is absorbed, a little bit distorted. So it is okay. So we then calculate the electronic band structure of the metal atom absorbed V2S2 sheet, and we see that the sheet prevails its metallicity, and in fact the metallicity has been increased. We can see from the density of state plot, its value is increased. So after doing electronic band structure calculation, we calculate the charge density difference calculation to get the idea about the electron transfer from the absorbed metal to the sheet. So this gives us this shows the figure on the left hand side shows the isosurface plot. From that we can see that the metal atom really give enough give enough electron to the sheet, and from the Bader analysis we can quantitatively calculate the amount of electron transferred from the metal absorbed to the sheet, which is tabulated here as well. Then we calculate the diffusion energy barrier calculation, and we found that for the lithium atom there is very small barrier. For lithium atom it is 0.41 electron volt. For sodium it is 0.12 electron volt, and for sodium it is 0.15 electron volt using CINEV calculation. Then we to calculate the capacity and OCV, we absorb more number of atom as much possible. So at first we covered with the monolayer, then we covered with the bilayer, then tetralayer and hexalayer, and calculate the absorption energies, and the absorption energy is tabulated here. And on the left hand side you can see the first row shows the top view and side view of the lithiated V2S2 sheet, that is geometrical optimized structure, and B shows the sodium absorbed V2S2 structure for monolayer, bilayer, tetralayer and hexalayer, and same goes for the potassium in figure C. So after calculating those absorption energy, we calculate the OCV calculation using this formula, and maximum capacity or storage capacity using this formula. And using this formula, we have plotted the open circuit voltage with the lithium or metal atom concentration. Then after getting the maximum absorption, we check the thermal stability of that structure using AIMD calculation, and we found that the structure is stable at both at 300 and 500 degree Kelvin. So here we tabulated the average OCV for the lithium absorbed, sodium absorbed, and potassium absorbed V2S2 monolayer, and we see that the average open circuit voltage for lithiated V2S2 is 0.68. For sodium, it is 0.71, and for potassium, it is 1.4 electron volt. And the maximum theoretical capacity for lithiated V2S2 and for sodiated V2S2 is 968.9 milliampere hour per gram. But for potassium, it is quite low, 322.9 milliampere hour per gram. And we also check the change of volume expansion percentage, and it is in the reasonable limit. So from this, we can say that this V2S2 monolayer, two-dimensional monolayer, can be used as a potential anode material for lithium-ion and sodium-ion batteries. So in summary, V2S2 monolayer as a highly efficient anode material for rechargeable monovalent ion batteries has been investigated theoretically using DFT VASP code. Metal atom absorbed V2S2 monolayer reveals that the metal atom atoms tend to preferentially intercalate on top of the buckled hexagon of the pristine V2S2 monolayer, preserving its essential metallicity. And exceptional energy storage capacities of V2S2 monolayer were showcased with high storage capacity of 968.9 milliampere hour per gram for both lithium and sodium, making it good choice for the energy storage application in lithium ion and sodium ion batteries. I would like to thank the organizer ICRTMD 2023 for giving me the opportunity to present my work here, and I would like to thank Professor Vikas Chandra Gupta, Vishwavarti Santiniketan, my colleague, and his project, TAR project with Dr. Hirok Chandra, and I would like to thank HPC HRI and also Professor Prosenjit Sen, HRI Allahabad, and thank you for kind attention. For your kind
Thank
attention.
you. First of all, let me thank the organizing committee for inviting me for giving a talk. Today I'm discussing high performance substrates for biomolecular detections. I myself is Jeslie Jacob from Department of Physics, Assumption College, Kerala. And let us start talking from surface enhanced Raman spectroscopy. Surface enhanced Raman spectroscopy or surface enhanced Raman scattering is a surface sensitive technique which enhances the Raman signal by the adsorbed particles on rough metal surfaces. This surface enhanced Raman spectroscopy is a result of chemical enhancement and also electromagnetic enhancements. But major contribution is from electromagnetic enhancements, and we are focusing now on the electromagnetic enhancements from enhancement side. So what happens is that laser light, when it falls on silver nanoparticles, surface plasmons gets excited, and this surface plasmons produces an electric field enhancement in the vicinity of the nanoparticles, and this analytes, they have a Raman scattering, and a re-radiated field will be produced, and they will combine together and will result in a surface enhanced Raman signal. That is what is happening, and this high sensitivity has many applications. That is, we are able to detect pollutants in the when we are thinking about the environmental analysis, and also it is a used as efficient cancer biomarkers in medical diagnostics, because it can even detect a very low level of cancer molecules in the human fluids. So it has many application in that area. Food safety, pesticide to detect pesticides and all, and in forensic science for detecting explosives, and so on going. We are discussing, or I am discussing on, especially on plasmonic SIRS substrates or plasmonic SIRS sensors, because plasmonic sensors itself are very have very high sensitivity, and when we are combining this plasmonic and SIRS, we will be getting very high sensitive sensors, which have many good applications in, especially in the cancer detection and all. So what is happening is that in plasmonic sensors, the electromagnetic waves get incident on metal nanostructures, exciting surface plasmons, and near field enhancement happens, and hotspots will be generated. And these in plasmonic SIRS substrate, what is happening is that incident light is incident on metal plasmons, and localized field will be produced, and the molecule near the plasmonic surfaces like analytes or any other cancer molecules or something like that, it will be scattering the light, that is Raman scattering will happen, and the re-radiated field and this enhanced field get combined, and then the amplified Raman signal is produced. That is, we are getting a molecular vibrational fingerprint. So it is very advantageous, because plasmonic coupling itself has a near field enhancement factor of the order of 10⁻³ and we are using the SIRS. The near field enhancement is reported up to 10⁻⁷ and 8, and we are getting more than that. What is happening in this electromagnetic enhancement mechanism? The incident beam, it is getting incident on the nanoparticle here. Nanoparticle will produce an enhanced near field around it, and the analytes around it will scatter the radiation, and re-radiated Raman scattering. This re-radiation process, re-radiated field will get combined with this enhanced incident field or the localized field, and an enhanced Raman signal is produced. So when we are thinking about, or when we are talking about the theoretical explanations, enhancement factor for the localized field is given like this. That is, the enhancement factor will be the ratio of the localized local field, that is a localized field to the incident field, and the enhancement factor for radiative field, that is the re-radiated field at the Raman scattering wavelength, will be equal to the ratio of scattering field and radiative field and scattered field. And thus we will get the final enhanced intensity of Raman signal as the square of these two enhancement factors into the incident intensity. But by classical theory of Raman effect, we know that if the incident wavelength and the Raman wavelength are closer, then approximately the enhancement factor of this radiative field will be approximately equal to the localized field. So we can combine it, and thus the SIRS enhancement factor will be the fourth power of the local field. And thus, the process can be summarized like this. Surface plasmon gets excited at the incident wavelength, and local field enhancement happens. And the polarized dipole creating scattered field at Raman wavelength causes a re-radiation process. They combine together to produce a SIRS enhancement factor of EF, and that is a enhancement factor raised to 4. So we are theoretically modeling the SIRS substrates, and so the substrate which is discussed in this work is a hexagonal nano disk of silver or gold. It is on the base of silicon dioxide, and we have taken trimer structure and improvise this into some arrays of pentamers and hexamers. And we have used finite element method using COMSOL multiphysics, and it is solved using the electromagnetic frequency domain and scattered field. So the material properties or the material parameters for gold and silver are chosen from the Johnson and Christie data, and silicon dioxide from Gao et al. Other parameters which we have used to optimize this trimer structure is that the side length of this hexagonal nanodisk is fixed at 50 nanometer and gap D equal to 5 nanometer. Thickness is about 10 nanometer. So we will just discuss the cell substrate optimization. We have taken the extinction spectra of, first we have taken a monomer of hexagonal nanodisk, and we have taken the extinction spectra. You can see that here a hot spot is formed at the corners, and this result in the extinction spectrum. And next we move on to dimer structures. Dimer structures show a little more local field enhancement because the plasmonic coupling between the closed faces of the adjacent discs and also the corners will produce hotspots, and this will give a more improved extinction spectrum. And moving on to trimer, it will have coupling from closed corners in addition to this, and this will result in more improved extinction spectrum. So now we have we are little more optimizing it or correcting it or testing it using the varying the gap between the discs. You can see here, first we have taken a dimer and the gap size is decreased. You can see here when the gap size is decreased from 7 nanometer to 2 nanometer, the extinctions or the field enhancement is improved or enhanced. Also, more hotspots is also visible. And again, moving to the trimer structure, you can see when the size is decreased, the gap size decrease will result in that is when it is coming closer, larger field enhancement is happening, and the narrow the gap, new plasmonic modes and increased number of hotspots, which means that it will improve the sensitivity much more. Now let's see what is the near field enhancement study of these structures, and we have moved on to, or we have analyzed more arrays of these structures. These are the near field enhancement study of first one is that of a gold trimer, and the second one silver trimer. Third one is the gold pentamer, and fourth one silver pentamer. Fifth one is a gold hexamer, and sixth one the silver hexamer. And also we have changed the orientation, that is the whole structure is oriented horizontally first in the y direction in the YZ plane, and we have taken the field enhancement study, and also it is moved vertically in the Z direction and taken the enhancement study. And summarizing, we can see that the trimer in horizontal orientation for gold it is giving 3 hotspots, but for silver it is 4 hotspots, and vertically also the same, but for pentamer it is horizontally it is 5 for gold, and for silver it is 10. That is much more improved and many hotspots. Vertically here there is 4, and here it is 5, that is silver 5 and gold is 4. Hexamer, again these are the results. And again, when we compare the results and the search enhancement factor, likewise, we can see that anyway, trimer and pentamer and hexamer are most best performing than monomer and dimer. And among them itself, the trimer vertical arrangement shows very good enhancement factor up to the range of 10⁻²². And we have analyzed using it using an analyte, that is how it detects an analyte. For that we have chosen a rhodamin 6G. This is a common analyte used in biotechnology for SIRS studies. It's a very good analyte. And so the near field enhancement of rhodomine on optimized silver trimer is taken for 600 nanometer, 710 nanometer, 960, 1070 nanometer excitation wavelengths. And we have just shown the enhancement factor here and changed the analyte concentration here. You can see that the analyte concentration, even in the small amount of analyte concentration, is giving a very good enhancement factor. So it is also evident from this that it can be detected from many other dyes. That is, even if there is many other dyes in it, it can detect rhodomine 60 particularly. So in conclusion, we have proposed research substrate. It is already published work. Hexagonal nanodiscs are proposed for sensing applications. And maximum enhancement by vertically aligned silver trimer is 3.662 into 10 raised to 12. And pentamer and hexamer, you can see that though the enhancement factor is a little less than silver trimer, it has a massive number of hotspots, which help us to lord and detect diverse target molecules utilizing the full 3D volume. And it is not much less. It is its enhancement factor is of the order 10 raised to 9 to 10 raised to 11. And the precise location of hotspots ensures the repeatability of the experimental results. Various concentrations of rhodomine 6G were detected using an optimized silver trimer with a maximum enhancement factor of 4.615 into 10 raised to 12. It is capable of, as I have already discussed, it is capable of detecting R6G in the presence of other dye molecules. It was offering a versatile platform for high quality source sensing, including biomolecule detection and food security. Thank you. These are some of the recent publications in the field of sensing. Thank you.
So, good evening, everyone. I am Dr. Jyoti Datta. I am currently working as an assistant professor in the Department of Chemistry, Dayanand Sagar College of Engineering, Bangalore. So, today I'll be talking about the influence of size and composition of... Sir, am I audible?
Yeah, audible.
Yeah. So I'll be talking about the influence of size and composition of carbonaceous nanoparticles on their fluorescence properties. So why we are always interested in carbonaceous nanoparticles? Because these are the generation of nanoparticles which are observed to have biocompatible nature, and they are non-toxic. Mostly they are obtained as a water-soluble nanomaterials, and they are easy for functionalization. Now, the fluorescence properties are mostly seen that these carbonaceous nanoparticles are generally having excitation wavelength dependent emission spectrum, and they possess good fluorescence quantum yield. Now, we have seen that in the previous literature, it is always dependent upon the method of preparation, the size of these nanoparticles, and whatever composition these nanoparticles are consisting of. Now, I would like to mention that in the present work, we have synthesized two different nanoparticles, and the composition of these two carbonaceous nanoparticles are varying because of the different additives that we have used. So we have opted for a hydrothermal synthesis procedure, and these nanoparticles are consisting of glucose. And the glucose is the major ingredient, and in one set of nanoparticles we are not adding any additive, whereas in the other set of nanoparticles we are using urea as an additive, and the medium for the synthesis is water. So the molar ratio that we have opted is 10:1. Then we have used autoclave with a oven temperature more than 200 degrees centigrade. We tried to switch to the different reaction time period. So we observed that if we have different combinations of this temperature and time, we have seen that there are different sizes of nanoparticles which are observed. So we observed that the nanoparticle solution which we got after the synthesis, it is a dark brown colored solution. And we have used syringe filter and dialysis method for the purification. So there is no further detailed purification procedure required for these nanoparticles. And these purified carbonaceous nanoparticles, which we have abbreviated as CNPs, are characterized by TEM, zeta potential, and UV and FTIR. So these are some TEM images and size distribution histograms for the CNPs. In the side, what you can see is the filtration method. So for this particular set of CNPs, what we observed is that from the same reaction mixture, we can isolate two different sizes using a centrifugal based filters, which you are seeing in the side. And the temperature for this particular carbonaceous nanoparticle synthesis was 200 degrees centigrade, and the reaction time was 2 hours. So what we observed that there are two sizes which we can isolate from these set of nanoparticles. One is 13 nanometer and another one is 33 nanometer. Now these two sizes were isolated in the two different filter region of these centrifugal filters. Further, the second set of carbonaceous nanoparticles, which was consisting of glucose and the NaOH was the additive. We have not used any urea here. So in this particular case, what we have observed that the size of the carbonaceous nanoparticles varied with the reaction conditions. So 15 nanometer carbonaceous nanoparticles was observed when the temperature was 250 degrees centigrade and the reaction time was 12 hours. However, we observed that the second set of nanoparticles, which are having 35 nanometer size range, they were obtained when the temperature was 250 degrees centigrade and the time for the reaction was 2 hours. Now, we checked the fluorescence emission spectra for these CNPs, and what we observed that these CNPs show a excitation wavelength dependent emission profile. So you can see in the figure that we have checked different excitation wavelength from 258 nanometer to 580 nanometer, and what we observed that the emission from these carbonaceous nanoparticles first increases with the increase in excitation wavelength, and it further decreases after 370 nanometers. So around 370 nanometer, we observed the maximum fluorescence emission intensity. And beyond 580 nanometer, they are not at all emissive, and we are not seeing any emission from this. Now, this kind of behavior was observed for all the four carbonaceous nanoparticles. And further, we checked for their fluorescence quantum yield. So you can see the fluorescence quantum yield for the two set of nanoparticles. All the four sizes has been shown here. We have opted for the measurement of fluorescence quantum yield using a reference, which is quinine sulfate. What we observed that the fluorescence quantum yield for these carbonaceous nanoparticles were not very high, they were moderate, and it was observed that the fluorescence quantum yield was size consistent. So for larger sizes, we were getting higher quantum yield. Now, if further we check the elemental composition of these carbonaceous nanoparticles, and what we observed that the composition of the carbonaceous nanoparticles which were prepared using glucose and urea, they were observed to have a significant variation, though they were isolated from the same reaction mixture. You can see the oxygen content as well as the carbon content for these two nanoparticles varied a lot. Now, for our purpose and to explore these nanoparticles further, we wanted to have a consistent elemental composition so that we can correlate their fluorescence properties with their composition and with their sizes and keeping the composition constant. So in the first set of carbonaceous nanoparticles where we were using glucose and urea, we observed that the elemental composition varied a lot. Though these two carbonaceous nanoparticles were synthesized from the same reaction mixture, were obtained from the same reaction mixture via filtration. However, for the second set of nanoparticles, which were synthesized using glucose and sodium hydroxide, the composition was more or less same. You can see the hydrogen elemental composition, the oxygen content, as well as the carbon content was in an appreciable range similar. Now we check the UV visible and IR spectra of these CNPs, and we observed that these carbonaceous nanoparticles, uh, here are the UV spectrum and the IR spectrum. So the carbonaceous nanoparticles consisting of glucose and urea were having major peaks of OH stretching and CH stretching, as well as there were peak for at 1629 centimeter inverse for C double bond O carbonyl group. Sorry. And in the second set of carbonaceous nanoparticles, which were consisting of glucose and sodium hydroxide, we observed that there are other functional groups. For example, we can see that 264 centimeter inverse for OH stretching, then CH stretching at 2976 centimeter inverse. There are also carbonyl stretching at 1779 centimeter inverse and 1716 centimeter inverse, which can be because of the presence of carboxylic groups. There are stretching, there are IR spectra at the stretching, the bending vibrations of CHC bond is also observed at 773 centimeter inverse and 925 centimeter inverse. So we can understand that these carbonaceous nanoparticles are containing multiple functional groups on their surface and probably in the bulk, because if we look into the elemental composition, the oxygen content is quite high for these carbonaceous nanoparticles. Now, further, since most of the reports on carbonaceous nanoparticles were already done for their linear fluorescence property and linear optical property, we were quite interested in probing the nonlinear property of these carbonaceous nanoparticles, for which we have opted for a second harmonic light scattering method. So this is a SHLS setup which was made in our lab. And here we have used an Nd:YAG laser with 1064 nanometer wavelength radiations. And we have guided this radiation from a couple of optics to our sample, which was further collected using a monochromator, and there was a photomultiplier tube for the analysis, for the detection of the signal. And we have checked that we should, using a probe para-nitroaniline, which is a standard molecule for optimizing the second harmonic. We have observed that the power dependence measurement, where we vary the power of the incident radiation and we check the dispersed signals, the scattered signal using the detector, and we have plotted the graph of the scattered second harmonic light intensity versus the incident radiation. And what we observed that the slope of this power dependence plot is 1.98, which is very close to 2. So this will ensure that the property which we are investigating, or the scattered light, is actually having a quadratic relation with the incident light. So further, I would like to show it in precise that we are incidenting the 1064 nanometer radiation on the sample of carbonaceous nanoparticles, and the scattered light, which will have a wavelength of 532 nanometer, was dispersed through a monochromator and was detected. And what we observed that for these carbonaceous nanoparticles, when we have dispersed the light from the disperse the incident radiation using a monochromator over the detector, what we observed that the second harmonic signal is associated with a multiphoton fluorescence background. Now this is checked for all the materials for which we check the nonlinear property, whether these molecules are also associated with any multiphoton fluorescence background. So in case of carbonaceous nanoparticles, we observed that the second harmonic peak, which is at 532 nanometer, is riding over a broad multiphoton fluorescence background of which is peaking at 570 nanometer. Now, if we consider to investigate any one of these, either the second harmonic peak or the multiphoton fluorescence peak at 570 nanometer, we have to remove the contribution from the other peak. For example, if we want to investigate the second harmonic peak at 532 nanometer, we should eliminate the contribution from multiphoton fluorescence peak at 570 nanometer and vice versa. So we have opted for a spectral fitting of these two peaks in order to remove the contribution of one peak from the other. So this is the spectral fitting which we have opted. This is a multiple peak fitting. And these are the two peaks, two line shape functions which we have used for this spectral fitting. Now, why we have opted for Lorentzian line shape function at for the peak at 532 nanometer and a Gaussian line shape function for the peak at 570 nanometer is because the scattering is an instantaneous process. So we expect that there should not be any broadening which is taking place for this second harmonic peak. And that is why we have opted for a Lorentzian line shape function. Whereas the multiphoton fluorescence peak is a broad peak, which can include many broadening mechanisms, for example, solvent broadening and the involvement of multiple excited and emissive states. So this is how we have separated the contribution of multiphoton fluorescence from second harmonic peak and the contribution of second harmonic signal from the multiphoton fluorescence peak. Now we have observed that the same property was shown for all the four carbonaceous nanoparticles. For example, for 30 nanometer, for 33 nanometer, as well as 15 and 35 nanometer, in both the cases, what we have observed is the second harmonic peak is always associated with a broad multiphoton fluorescence background. The only difference that we can observe in these four nanoparticles is the contribution of multiphoton fluorescence peak is lesser in 35 nanometer carbonaceous nanoparticles. Now, this is a matter of further investigation. So we check that whether the contribution is because of one photon or the two photon or multiphoton fluorescence. So we first looked into the linear fluorescence profile of these carbonaceous nanoparticles, and we observed that all these nanoparticles are not showing any fluorescence at 570 nanometer, and there is no emission at 570 nanometer. So this ensures that it will not be a fluorescence due to a linear fluorescence property. Definitely it should involve multiple photons for the fluorescence property. Now
Hello,
in
doctor,
order to
please
check,
finish.
yeah, yes,
Please finish.
hello.
Time is over. Huh? Just
Okay,
finish
okay,
it.
sir.
Huh? Time is
I'm just concluding it. So we have measured the power dependence plot for these carbonaceous nanoparticles to ensure whether it is a multiphoton fluorescence, and if it is a multiphoton, whether it is two photon or three photon fluorescence. So for the power dependence plot, we observed that the slope of the power dependence plot is 1.95, which ensures that the multiple photon fluorescence that we are observing for these carbonaceous nanoparticles is actually a two photon fluorescence. Now, in conclusion, we would like to mention that these carbonaceous nanoparticles are not showing very high fluorescence quantum yields, and these quantum yields are having dependence on the size and composition of the synthesized carbonaceous nanoparticles. Further, we can see that these photons have very broad multiphoton fluorescence background. So we can say that in addition to linear properties, they are also having non-linear properties. So they can be explored for both one photon as well as two photon fluorescence spectroscopy based application. Further, they are strongly scattering the second harmonic light. So they must be explored for the beta measurements and further details. So I would like to acknowledge Department of Chemistry, Dayanand Sagar College of Engineering, and where I am currently working. I am also very thankful to Professor P.K. Das, who is my postdoctoral advisor, Department of Inorganic and Physical Chemistry, IISc, where I have carried out these works, and my lab mates. Further, I would like to thank sincerely to the organizing committee for giving me a chance to present my work. Thank you all.
Thank you very
I would
much.
be